Hello, this is Laura Fulford welcoming you to this Bite-Size Bio web seminar, which today is sponsored by Zeiss. Today's presentation is titled Zeiss LSM800 with Eriscan, your compact confocal power pack. Confocal imaging demands the very best imaging quality. With LSM800, you choose a flexible and compact confocal laser scanning microscope, complete with highly sensitive GASP detection and fast linear scanning. Add Eriscan, the revolutionary detection concept from Zeiss, and push sensitivity beyond the limits of all conventional confocals. Today's seminar is presented by Chris Power, Zeiss imaging specialist. Chris studied biology and oceanography at the University of Southampton and became the product manager for confocal systems at Biorad from 2000 to 2004. Afterwards, he moved to Germany to develop confocal and light sheet technologies at Zeiss, including a project leader position for LSM700 and LSM800. In 2011, he moved back to the UK to become a 3D imaging specialist. We will have a brief question and answer session after the presentation. Any additional questions will be answered in a PDF document made available along with the on-demand webinar. Please type any questions that you have into the questions box, which appears on the right-hand side of your screen. So now over to you, Chris, for the presentation.
Okay, so good afternoon, everybody. So I will run through the presentation today of the LSM800, which is the kind of little brother to the LSM880 we recently launched. This afternoon in the talk, I'm going to run through very briefly the motivations behind why we've generated this, this 8th generation of confocals. I'm going to cover a new technology within the 8th generation called Eriscan, which applies both to the LSM800 and the 880. And then finally, I'm going to cover some of the specific details behind the LSM800, how it's implemented, the scan head, etc. So if I just start on the motivational side, confocals today have really evolved over the past 30 years from just point scanning imaging systems to a very flexible, versatile tool. Now, some of that, of course, is still based on imaging, so be it 3D, be it time-lapse, multicolor, and so on. And some of it's a little bit more dynamic. You've got techniques looking at molecular diffusion rates, how things move about in your cell, techniques like frets and fraps, and so on. They've really become quite a versatile tool. And as they expand, we wanted to go to our customer base and ask, what do you want to see moving from the 7th to the 8th generation? And when we question people, what's the key feature? We got the result shown in the pie chart on the left here. And there are a couple of features about ideas on new features we could put in, but predominantly the main areas of improvement are what we normally call in confocal circles the kind of holy triangle. This is speed, resolution, and sensitivity. And because they're the key components in any imaging system, it was no surprise that they're where people want to push the boundaries. And so really that was the main focus behind the 8th generation. How do we improve the speed, the resolution, and the sensitivity? So how did we address that in the 8 family? Well, in the 8 family, I already alluded to, there are 2 models. There's the LSM800, which is the compact version, and the LSM880, which is the higher end model with a few of the more unique and niche features available on it. However, these 2 systems we developed together. It was a technique that worked well with the LSM700 and the 710, the previous generation. It's a technique that we believe has worked well now. The reason why we developed these together is we wanted there to be a good span in the market. It's very hard to design a product that goes all the way from the entry level to the high end. So we felt it was necessary to have 2 products. And yet, any effort you put into R&D on how to improve these, we want to be able to utilize. So all of the work that went into the 710 on improving the optics and getting the very best from the system, we were able to utilize on the 700. And now on the 800, we're doing the same thing. The first feature that is common between the two systems is fast linear scanning. So what is fast linear scanning? In a point scanning system, you move your scanner across the field of view. So you have different pixel dwell times as you move across. The key to linear scanning is that each of the pixels are treated equally, scanned equally. So as you park or as you move your laser beam across the field of view, you want the time that your laser is on pixel 1 to be the same time as it is in pixel 256 in the middle of the field of view, and the same at the last pixel at the end. In that way, it's the most time efficient and it's the most quantitative. The other thing you want is a very good duty cycle. This means you want to spend most of your time scanning and not much of your time in the turnaround periods at either end. And the reason you want that is it means on average your laser power is lower for any given pixel dwell. So less photo damage, less photo bleaching. There are techniques where you scan using a sine scan. So that's where you just kind of wobble or shake the galvo left and right across the field of view. But when you do that, you can end up with uneven pixel dwell times and not as high duty cycles. So we wanted a fast scan regime. That's what we've designed in the 7 series. It's what we've sped up in the 8 series, and that's common to both the 800 and the 880. The next thing that is common for both of the systems is gallium arsenide detection. So gallium arsenide phosphide detection, it really refers to the alkali pair used on the front of the photo multiplier tubes in the systems. Gallium arsenide phosphide is not new per se, but it's reasonably new that they're becoming so widely used, and it's unheard of for gallium arsenide phosphide to be really put into an entry-level system. So with the LSM 800, we've introduced gallium arsenide, really the high-end technology from the 880 into the 800. When we talk about detectors, I just wanted to kind of highlight the key differences between the two systems. The LSM 700, the previous model, was based upon 2 multi-alkali detectors. The 800 starts in the same place, so it kind of starts where the 700 left off with those 2 multi-alkali detectors. However, you can now have 2 gallium arsenide detectors. You can also have the option of a third channel. The third channel can either be based upon multi-alkali, gallium arsenide, or Airiscan, which I'll describe in more detail later. The LSM 880 has a single gallium arsenide detector which has 32 elements in it, so 32 gallium arsenide for single shot spectral imaging, and it has the option of the Airiscan. So similar underlying technologies, but different number of detectors in total. The third thing that's common to the two families is Airiscan. Now, Airiscan is an interesting new technology, and it kind of rides upon the need at the moment to increase resolution. As some of you may know, in 2014, the Nobel Prize for Chemistry was awarded to super resolution within the life sciences. Now, there are many different techniques for doing super resolution. Zeiss already have super resolution techniques available to do structured illumination and photoactivated localization microscopy. However, as amazing as these techniques are, a lot of them have only been available to selected labs because you have dedicated machinery. And what we were pondering with the development of the 8 series is whether we could make it more mainstream and more widely available. To do that, we went back to basics. At the heart of the confocal, you have a pinhole. So the system scans, you have your laser coming in, down to your sample, and on the return path, we pass the light through a pinhole in order to remove the out of focus light. This is very basic, has been since day one of confocal. If you look at how that pinhole works and how it rejects light and transmits light, what you see is that there is an airy pattern that you have to decide how much of to capture. And you have to somehow pick a compromise between what goes through and what does not go through. And we typically do that around 1 area unit. What this means in practice is that you have a molecule, you have a laser spot, and as you scan over that laser spot, you choose how much signal to collect and how much to throw away in order to get your rejection. The idea of using 1 area unit has been around kind of forever, but to use less than 1 area unit was really just not done, not used. But there is a book that's widely available called the Confocal Handbook of Microscopy. This book's been around for decades, and within it, it does point out that if you close your pinhole under 1 area unit, you can increase resolution. You can increase it up to 40% over the Abbe limit. But to do that, you have to throw away most of your light. And so most people just have never done this. There's not enough light available in typical biological imaging. These graphs really kind of drive home that point. The top left graph shows the pinhole diameter versus section thickness. So what confocals are really known for, closing the pinhole to close down the section thickness. The top right-hand graph, however, shows that you can get a resolution increase if you close your pinhole under 1 area unit. You get diminishing returns under about 0.2 area units, but you do get returns. The reason why we don't do that is shown in the bottom right graph. In the bottom right graph, you see the transmission as you close your pinhole down. So 1 area unit really is that kind of sweet spot between between getting a good section and good resolution, but also having enough signal to image. Now, if you were to close down the pinhole, you would get better resolution. But as you can see in this cartoon here, as the beam scans across, you'd end up binning most of your light. Most of it would be rejected by the pinhole. So what we have introduced in the AIRI scan is a hexagonal array of detectors, each of which comprises 0.2 area units, and in total they cover an area of 1.2 area units. So now as we scan across, we collect light not just on one detector, but on a number of detectors. And the reason for that is to try and kind of overcome the traditional detection threshold. So rather than collecting all the light with 1 area unit, where you get a decent signal to noise, or 0.2 area units, where you'd get improved resolution, but with limited signal to noise, we're going to do this technique called AIRI scanning, where we collect on lots of different elements. Now, to explain that in a little bit more detail, I'd like to show you an example based on sub-resolution beads. Here, you see an image which was acquired with 1 area unit of 170 nanometer beads. So 170 nanometer beads are below the typical resolution limit. If you acquire that, and instead of using just a 1 area unit pinhole, you use small offset colored pinholes, you get an image like this. You see each of the beads kind of offset slightly and in different colors. This is really just a slide to illustrate the principle of what I will now explain. If instead of using a 1 area unit pinhole, we replace the pinhole with the AIRI scan, here you see each of the elements of the AIRI scan detector. So you see element 1 in the middle, and then additional rings going around until we have 32 rings. If you look at the light that is acquired in the first ring of detectors and you image those beads, you see a pattern like this. So I hope you can now see that the beads are kind of rotating round. This is the image acquired by each of the 6 elements in the first ring. Now, if you were to average that light, just a simple average, you then get the image on the right. If you now consider the next ring out, the third ring, or sorry, second ring, I should say, from the middle. If you then look at the light acquired by this ring, you have a weaker signal because it's further from the middle. You have a more pronounced rotation, and if you average that, you get a blurrier image of the beads. And again, if we then take that to the third ring, the outer ring, you get an even more exaggerated movement, even less light, but you still do get light. And if you average that, you'd get a blurrier image. So if I then show the kind of averaged or integrated image amongst the central spot of the Airy scan, the next ring, and the last ring, you see these 3 images. And what I hope you see is that the image kind of apparently gets blurrier. There is a bit more signal in the second and third ring because there's more light cumulatively, but it gets blurrier. Well, that's kind of what happens when you just use a 1 area unit pinhole. You just acquire all of this light, so you get more light, but it's blurrier. However, we can be smarter than just summing the signal here. Because we know where each of the 32 elements are, and we know where it was detected, we can digitally shift the light so that it no longer has this rotation as we play through the elements. It's shifted and aligned to the central element. If we do that for each, both the middle dot, the middle dot has no reassignment, but if we do that for the first ring, the second ring, and the third ring, you see the images on the bottom row here. And what you see is that they all end up with comparable resolution. You get a lot of signal from particularly the second and the third ring. You may even see that the third ring, whilst a bit dimmer, has the best resolution of all, because the misaligned pinholes, or the offset pinholes at the side, actually have an increased resolution effect, however minor. So we have all of this information. What do we do with it to form the final image? Well, before we do the alignment, we deconvolve each of the 32 elements. We then shift and align those together, and we form them into the reconstructed image. So if I show you finally an image of these beads, the left image is 170 nanometer beads acquired with confocal. The middle image is the same beads acquired using the Airy scan and applying the pixel reassignment method. So just by shifting the data about, we get this improvement of about 1.4-fold. And then if we apply deconvolution on that, we can push that to 1.7-fold improvement. So this is a particularly noisy example, but what you can see is on the left in confocal imaging, you just don't have the resolution to see these beads. And with the Airy scan technique, we can pull these apart. So the process is pretty simple. It really is just a linear deconvolution applied upon each of these 32 elements. This will give us a 1.7-fold improvement in X, Y, and if we do a Z stack, also in Z. One key point I would highlight here, we could just try and close the pinhole and deconvolve, and you could try that on a normal confocal. But by doing that, you only end up with the light that would have hit one of these 32 elements, not all of these elements. So if your sample's infinitely bright, then sure, that will work. But with a real biological sample, that's just not feasible. So now we've got this improvement of 1.7-fold. Well, that's all fair and well on beads, but beads aren't very exciting. So when we finally took this out into the real world, this was one of the first images we acquired testing the unit. And here you see on the left a confocal image taken with gallium arsenide phosphide detectors, and an image on the right taken with the Airiscan of mitotic cells. So that really kind of summarizes the main features that are common to the LSM 800 and the LSM 880. It's the faster scanning, the sensitivity of gallium arsenide, and then the Airiscan for super resolution imaging. If I go a little deeper now, I just want to highlight some of the differences and the features of the 800 itself. The 800 itself was really designed to be what we call a workhorse, so something which covers 90–95% of the routine imaging applications, but does it extremely well. To do that, I'm going to run through how we can tailor it to meet imaging needs, how it has some open interfaces, and really why this compact system is a high-end confocal system. First of all, in terms of tailoring, here we see the light path of the LSM 800. The two detectors at the top are the PMTs, which can be multi-alkali or gallium arsenide. Gallium arsenide gives about a 50% increase in quantum efficiency. It varies depending on where you are in the spectrum. So under 400 and over 700 nanometers, it gives you no advantage. But in the 500–600 nanometer range, you get this doubling. And why that's relevant is really how you think about sensitivity over time. Over the past 30 years, confocal microscopes have got more and more sensitive. The graph here shows how sensitivity has improved over the years in confocals, and here on the right you see both the LSM 800 and 880 if we use multi-alkali detectors, and the LSM 800 880 if we use gallium arsenide detectors. One interesting thing if we look at the sensitivity of a system is we can play an interesting game where, as we look at the light path within the confocal, we look at where sensitivity is lost. And we do this all the time. We try and refine each and every element. So the galvanometers, we've changed the coating so that they're now 99% efficient. We changed the main beam splitter so that it's also high 90% efficient. And you can go through each and every element within the system and ask, well, what if it was 100% efficient? Because we can't be 100% efficient. In 1,000 years' time, if we're still building confocals the traditional way, we have an endpoint. It's when everything is 100% efficient. Well, if you do that and you plot it on a typical signal-to-noise experiment, that's what we see here. That's the ideal system on the right, that we can. It's the best we can be doing things the conventional way. And so, actually, the line's in slightly the wrong place, but what we should see here is that the gallium arsenide takes us to about halfway from the introduction of confocal to the ideal system. The reason for that is really that we have strived to improve every element of the beam path here. I mentioned we've improved the coatings on the galvanometers, we've used narrow angle main beam splitters, which are very efficient, but we've really gone through each and every element here. The LSM 800, like the 700 before it, has a very efficient beam path. There's not much to it other than that necessary to get a confocal image. One element which is unique to the LSM 700 and 800 is something called the VSD. So VSD stands for variable secondary dichroic. This is the technology which allows the light to be divided amongst the detectors. The technology itself is a piece of glass substrate. It's probably 2–3 inches long, and it's as shown at the top of this slide here, where there is a mirror on one end, there's a plate or a transparent region on the right-hand side, and then in between it has a gradient coating. And that gradient coating acts like a long pass filter. So if you shine light to the left-hand side, it will transmit light transmit light over the blue wavelengths. If you shine light at the middle, over the yellow wavelengths, and to the right over the red wavelengths. So by shifting this VSD along the light path, you can choose which light is diverted to a detector or not. In the LSM 800, we do that not just with one VSD like we did in the 700, but also with two VSDs. So we use one variable secondary dichroic as a long pass filter and one as a short pass filter. And this lets us also divert light to an optional third channel. So that third channel could be a multi-alkali or gallium arsenide PMT, or it could be the it could be the Airy-Scan. So just to kind of fly through the beam path here, I hope this animation works over a webinar. Here we see the excitation laser going through on the main beam splitter to the galvos and to the microscope. The returning emission comes back through those scanners, goes back through that main beam splitter, through the pinhole, off the VSD, through an emission filter wheel and onto PMT1. The emission filter wheel is optional. We're already at the main beam splitter block enough of the laser light that you can choose whether or not you want that. By moving the VSD, we can then divert light to the second channel, where again we can choose to pick out a certain region. And if we move the second VSD, we can then send light, as shown here, to the Airy-Scan. So by moving the position of the first and the second variable secondary dichroic, we can fully tune the start and stop wavelength that we detect in the third channel. So this means that the Airy-Scan in the LSM 800 is fully spectral tunable to wherever you want to be in the wavelength. So that's the light path. When we talk about the Airy-Scan here, the Airy-Scan used in the LSM 800 is pretty much the same as that used in the 880, but it's slightly different. The Airy array itself is based on the same 32 elements. So these are 32 gallium arsenide detectors. The image quality we get from the Airy-Scan has the same resolving power, so the same resolution and the same sensitivity boost as in the 880. We can do multicolor imaging using the Airy-Scan, but to do that we go sequentially. It has the same depth penetration as on the 880. So an important point here is that the Airy-Scan is a super resolution technique that works not just with samples that are 5 or 10 microns thick, but deep into living samples, 100 microns or so. And it will work with living samples. It's a very, very gentle super resolution technique, so you can use it without fear of kind of blowing holes in your sample from very high laser powers. You can, if you don't want to do super resolution, if your sample doesn't necessitate it, you can just use the Airy-Scan as a third channel, a third gallium arsenide very sensitive channel, but just a third channel. Probably the biggest difference with the Airy-Scan in the 800 is to try and keep the pricing attractive for a kind of workhorse system. There is no zoom optic. So there is a zoom optic in the 880, there's not in the 800, and that means when you buy the system you have to decide which objective lens you would like the resolution gain on. So be it 40, 63x, etc. So here I just wanted to show a couple of images acquired with the LSM 800. The first is a spinal nucleus from a mouse, and here this was acquired by a group who routinely imaged these samples with an LSM 700, and they commented, of course, that the image quality is much nicer now with the gallium arsenide detectors. The second image here is again a mouse brain sample, here looking at thigh neurons and oligodendrocytes. Here we have some neurons again. One point I point to here, this is highlights well that with AiriScan you can do multicolor imaging just by sequentially imaging each of the three colors, and you get the resolution increase for each of the three colors here. This is an example 3-color again using HeLa cells, and you can see here the image on the left was taken with the gallium arsenide, the image on the right was taken with the AiriScan, and you can see the resolution increase and the signal to noise increase, but I'm just going to zoom in on a region here so you can really see some of the differences you can get using the AiriScan technique. The next example here are some chlamydia centrioles, which are very, very small and quite hard to pick apart. Here you can see the difference the AiriScan makes. Here's some mouse retina. So this shows you can do super resolution not just of kind of wafer thin samples, but also at some depth. Here we see a Z stack that will play through from Drosophila brain. And then the final example here is some epithelial cells from pig kidney. And this is highlighting the fact that you can use AiriScan on live samples, still get the resolution increase, and do that with gentle enough laser power that your sample divides. Okay. The next part of the LSM800 I'd like to highlight is what we call open interfaces. So these are ways in which you can expand the capability of the system. The first part of that is that the LSM800 we now run using the ZenBlue software. So this is the software we traditionally run a lot of the wide field imaging systems from. By moving to that, we have a very advanced experiment designer. So we have a lot of advanced functions for doing complex multi-stage, multi-location, multi-parameter experiments. A lot of those have advanced tiling functions. You have a huge amount of image processing controls available from our wide field platform, and you have very powerful camera control. So if you want to integrate your experiments with a wide field setup, you can do so. This has already increased the power of the 800 somewhat, but the next part of this is we have exchange with third-party solutions. What this means is we have something called the OAD, or the Open Application Development. This is a Python-based editor, IronPython for those of you who know the difference. The Python editor is a very powerful but friendly interface for you to write your own scripts to run within the Zen environment. Now, a simple example of those would be to automate processing available within Zen. So if you just want to automatically run the same processing routines to maybe filter your data, do some basic cell counting, and so on, you can automate that. Where OAD really gets powerful is that you can then branch out and utilize other programs. So say there's an interesting processing function that's just become available in Fiji, ImageJ, or something available in your Omera setup, maybe something in MATLAB you've been working on. You can take your images acquired within the Zen environment and you can pass those across to a third-party program, run your processing routine there, and then bring it back to within the Zen environment. So you don't have to reinvest twice to use processing techniques that have been developed elsewhere. The epitome of this, the high end of this, would be to do something that we call experiment feedback. So you could, for example, take those images, pass them to a third-party program, analyze them, bring them back, and then change your image acquisition based upon the result. Now the options are kind of endless here. Just as a brief example, if you were imaging multi-well plates, you could, on the first run over your multi-well plate, pass the images across, do some processing, and work out, are there any cells in this well? Are there enough cells to justify me coming back here? And if half of your wells haven't worked, there aren't enough cells there, on the second and third and subsequent runs through the acquisition, you could just ignore those. That's the kind of thing you can do with this powerful experiment feedback. Another example of open interfaces on the LSM 800 is something we call shuttle and find. Within Zeiss, we now have the broadest range of any microscope company, in that we cover all the way from the kind of centimeter scale right down to the sub-nanometer range with the electron microscopes and everything in between. If you have such a broad range of systems, it's quite possible you might want to look at your sample on more than one. And when you do that, you might want to correlate the results. Well, shuttle and find is the option to do that, where you take a sample from one microscope, you move it to another one, and you find the same cell, so you can correlate your images. The last point I really want to highlight on the 800 is just, it's a compact system, but it does have this high-end imaging performance. And for that, I wanted to kind of jump back to and show an example slide from the Airiscan. Here we have a selection of images taken of some microtubules on a gallium arsenide system. So the left-hand 4 images were acquired using gallium arsenide. Some of those were taken with a single image, and some of them are taken with an average of 4. So I hope you all know that if you average images, because you scan them multiple times, you increase the signal to noise. The top row of images here was acquired using 0.2% laser power on the 488 line. The bottom row of images was acquired using 0.02%, so a tenth of the laser power. I said the left-hand images were acquired using gallium arsenide. The right-hand 4 images were acquired using the Airiscan. I'm going to zoom in here so that you can see some of the details, and we can start to really see the benefit of the Airiscan. If I draw your attention to the top 2 middle images, what you see here is the gallium arsenide with an average of 4. If you compare that to the Airiscan with a single image, you see that the Airiscan has much better signal to noise and resolution, despite being taken with a single scan as opposed to an average of 4. This shows you that the system, because you'd need to scan 4-fold at least to keep up, it means that the signal to noise benefit is at least 2-fold with the Airiscan. Okay, that's easy enough. If you compare the gallium arsenide average of 4 with the bottom right-hand image, so the Airiscan average of 4, but with 10% of the laser power, you can still see that the gallium arsenide has an improvement in signal to noise and in resolution. So you still have a benefit even with 10% of the laser dose. And that means you've got at least a 3-fold increase in signal to noise ratio. And in the extreme case, if you look at the gallium arsenide with weak laser power and with no averaging, you see the image begins to get to a point where it's just snow. You can no longer see anything. And yet the Airiscan with a single scan and low laser power, whilst it's not the prettiest image on the slide, you can still get meaningful biological results out. So what I'm showing here is that the Airiscan signal to noise wise is of the order of 2 to 3-fold more than the conventional detector, even based on gallium arsenide. So if you think back to the slide I presented earlier that shows how sensitivity has increased over time, if we imagine, well, don't need to imagine, we've seen how much of a signal to noise increase the Eriscan gives over gallium arsenide. It means that on this graph, the Eriscan systems are better in terms of signal to noise than an ideal system. So this means if you have Eriscan, you can get images that would be better than if you had a system that was 100% optimal. If everything in your light path was perfect, if your PMT was 100% sensitive, the Eriscan would still outperform that system. Now, does it mean that we've broken physics? Of course not. All it means is that our ideal system now, we've redefined the goalposts, and now the ideal system is 3-fold higher than what's shown here. So if ever we get hold of a 100% quantum efficiency detector, we could be 3 times higher here. But for now, the Eriscan is the only way to be that sensitive. And that technology is available in the compact system, in the LSM 800. So what I hope I've shown throughout the talk here is that the 800 has all you need to get the best of your sample, the best image quality, the best resolution, best sensitivity in a very small, affordable system. It's very easy to use, it has a very small footprint and low energy, and therefore it's going to be a real nice workhorse to go into either an individual lab or to supplement a core facility. The open interfaces via OAD, the experiment designer, and camera controls will allow you to have a multi-purpose system. You could really customize this thing to run through many samples, and the possibilities are endless here with the open interfaces. And finally, I think you'll find that we have a very flexible system. You can take the LSM 800 from a 2-channel system all the way up to 2 gallium arsenides with AIRI, with the fast linear scanning, and with all of the image quality benefits I've mentioned. So with that, I'm just going to finish with a couple of comments and recommendations that we've had for the 800, and then finally leave you with a slide that refers to some further reading. So a couple of websites, either directly to the LSM 800 or to the Eriscan, or at the bottom the confocal principles booklet, which describes that relationship between pinhole size and resolution. And with that, I'm finished.
Thanks, Chris. That was a really good presentation. So thank you so much for that today. We have a few questions, and I'll just get started with those. If anyone else has a question, please pop them in the questions box that appears on the right-hand side of your screen, and we will put these in a PDF and make them available along with the recording that should be on our website within the next 24 hours. So to begin the questions, regarding the LSM 800 and the LSM 880, where do you see the most appropriate application fields for each instrument?
It's interesting. In many ways, they overlap quite strongly because the LSM 800 was designed to have the same performance as the 880. I think where the 880 really kind of takes over from the 800 is in the more advanced and the more niche areas. So partly it has a broader range of laser lines. So the 880 has UV options, has more lines in the middle, such as 458, 515, 594. Multi-photon options are only available on the 880. You have that ability to do simultaneous complex unmixing of overlapping fluorophores, and you also have the numerical techniques. So by that I mean things like FCS, FCCS, RICS, correlation techniques. So yeah, I'd kind of say the 800 and 880 overlap a lot, but for the more advanced features, yeah, the 880 has a few more tricks up its sleeve.
Okay, thank you. The next question is the ARES scanner detector in any way limited in comparison to the LSM 880?
A little bit. So on the basic things, the things that really matter. So for that, I would say the sensitivity and the resolution. So this improvement of 1.7 fold in X, Y, and Z. The performance on the 800 and on the 880 is identical. The one advantage of getting the one advantage of getting the ARES scan on the 880 is speed. It can go about 5 frames a second as opposed to 1.6 on the 800. And also on the 880, you can use more objective lenses with the ARES scan. The ARES scan should work with most objectives, but with the 880, we really get the most out of every lens. Whereas with the 800, you have to think a little bit in advance about which lenses you'll use it for. Okay.
Okay. And how much more sensitive is the GASP and ARES scan option compared to the LSM 700 with PMT?
Okay. Well, to go from the 700 to the 800 with gallium arsenide, so it's roughly the difference between multi-alkali and gallium arsenide, which is about a factor of 2 in that mid-range. And then if you then went to ARES scan, you get about another factor of 2 to 3, as I was showing on those microtubule slides. So to go from the 700 to ARES scan, somewhere between kind of 4 and 6-fold an improvement.
Okay. And are there incubation solutions for LSM 800 and an option for wide field camera support?
Yes, absolutely. The stands we go on the Axio Imager and the Axio Observer, so our standard upright and inverted systems, and we can use, I believe, most of the incubation options for those systems. In terms of cameras, now that we run the LSM 800 in Zen Blue, we have the full range of cameras that we support on all of our wide field systems. So a big range.
Okay, that's all we've got time for today. Thanks again, Chris, for a fantastic presentation and a really lovely discussion. And thanks also to our sponsors, Zeiss. Finally, thanks to you, the audience, for taking the time to attend and listen in. If you had enjoyed this webinar and would like to view the video recording of the session, please visit the webinar page on bitesizebio.com, where it should be available within the next 24 hours. You can also see other webinars that we have lined up for you in the Bite-Sized Bio Webinar Festival, including a final webinar by Zeiss on Friday. So until next time, good luck in your research and goodbye from all of us at Zeiss and Bite-Sized Bio.